So at this stage, we all have R installed on our own personal machines. We've got Easy installed, and we've got this data set in the Project 4 folder that we want to take a look at. So I haven't read in the data yet, so what I'm going to do is select all my code to read in the data, run it, and it will have read in the data. And I can confirm that the data is read in by looking at it. I can look at the first. Oh, it's gone awry. That's because I haven't set my working directory. I know that simply because up here you've got // which is the default working directory, but I know I want it to be in Project 4 analysis. So I'll click the wheel, set as working directory, and then I can reselect the code to read in the data. And then rerun the code to look at the head. And I see indeed I've got some data here. If I want to actually look at the full data object, I can click the Workspace tab and click the actual data object A, which is just an arbitrary name in which I'm storing that data. And I can see that it's this big data frame, 12,000 observations, 10 columns. I'll just close that. Another way of getting a summary of the data set is to run the easy précis function, which if I run it, oh, it's wrapping. So I'm going to increase my window size a little bit here so that it doesn't wrap, and run that again. There we go. Looks nice. So for each column in the data set, I've got a row here, and the row gives me information about what's going on in that column. So ID is numeric. That's presumably the subject ID. We've got another column called group, and that's a factor. It has two levels. One level is called TD, the other level is called ADHD. So this seems to be a experiment where we had two groups of participants, some that are typically developing, some that are that have a diagnosis of ADHD. Got a column called age. And it seems to go from 18 to 25. So looking at a college age participant group here. Column called sex. It's being treated as a factor. It's got two levels, male and female. Got a column called block. It's numeric. It has 10 unique values, and the first one's 1, the last one's 10. So presumably block goes from 1 to 10. Ditto trial is numeric, 32 unique values, probably 1 through 32. Now we have a couple what look like to be experimental variables. Dot, which is a factor, two levels, invalid and valid. Arrow, which is a factor, two levels, invalid and valid. We've got two performance variables, reaction time and error rate, or whether somebody made an error or not, so it's just ER. So if we just glance up to when we had head of A, you see that the reaction time is looks like it's milliseconds, and the column with ER in it just labels things as either 1 or 0, whether they have made an error or not. Reaction time, minimum reaction time is about 250 milliseconds, and the maximum is about 800 milliseconds. So yeah, this data is coming from just a fake experiment that I made. It's a typical type of thing that I do, which is lots of observations from each of multiple individuals. I've got a between subjects manipulation of group. In fact, it's not a manipulation, it would be an observed variable because it's a diagnosis, so presumably I can't assign diagnosis. But another observed variable, sex, might be something to look at. Another observed variable, age, might be something I'd use as a predictor variable. But dot and arrow are both manipulated variables. They're features of the task that somebody has. What I was imagining here was each person participates in many trials. Each trial has a dot that appears on the screen, and an arrow that appears on the screen. The arrow tells you where a subsequent target's going to be. The dot doesn't tell you where the subsequent target's going to be, but so an arrow appears along with a dot, and then a target occurs. And participants are supposed to respond as quickly as they can as soon as they see the target. The target clearly is a discrimination choice, so they could get it right or they could get it wrong. So imagine they have to, they see a plus or an X, and they just have to say plus if it's, press this hand if it's plus, press this other hand if it's an X, and so you get accuracy as well as reaction time with that. So we see that we've got two levels of each of these variables, dot and arrow. We've both got valid and invalid. So presumably the valid trials are where the valid arrow trials are where the arrow pointed to where the target was going to be. Valid dot trials are where the dot actually appeared where the target was going to be. Invalid dot trials, the target appeared at the opposite location from where the target was going to be. And invalid arrow trials, the target appeared at the opposite pointed location as the arrow was pointing. So this is the type of data that I typically encounter. I've got a couple within subject variables, maybe a few between subject variables, and I'm interested in usually reaction time only for those trials where they made accurate responses, but I might also do an analysis of error rate itself, the rate at which they make errors under the different conditions. The first thing we'd want to do in this scenario, though, is ID. This is the unique subject identifier label. Should be a factor. Right now it's being treated as a number. As we can see here, it's numeric. So what we probably want to do, first thing is to fix that. So I've got this little piece of code here where I say AID. So I'm replacing the contents of that column with whatever's on the right-hand side of the equal sign, which is simply a factorized version of what was in that column originally. So I can run that, and if I run easy précis again, it'll show that that column is successfully being factorized. I'll copy easy précis and run it, and indeed now ID is a factor. Other functions will complain down the line if we fail to do that. So it's a good idea to always turn those columns that should be factors into factors. Now let's get just a visualization of the sort of balance of data that's being collected. So we're going to use the easy design function, which will create a graphic. The easy design function, we're going to give it 3 named arguments, data, x, and y. The value provided to the data argument is just a data frame that we want to look at. The value provided to the x argument is a column within the data frame that we want to just put on the x-axis, and the value we give to the y is the column in the data frame that we want to put on the y-axis. Anytime you do an easy design, you have to look at least 2 columns, one to put on the x and one to put on the y. In the easy that you have installed in your computers right now, it definitely wants to have the period parenthesis around whenever you refer to a column within the data frame, you need to put this period parenthesis around it. It's just easy's way of saying this is a column within the data frame that I previously specified. So I'll run this first little call to easy design. It should give me a plot that will appear automatically. Interesting. I get a warning. Yeah, everybody's going to get a warning. Pardon me? Yes, exactly. So the warning doesn't. It's a warning to me as the developer of Easy that the version of Easy that you guys have installed and is on R uses another piece of software to do its graphics, and I've used a slightly older way of doing things in that software that's not wrong right now, but eventually it will be removed. So I need to, me as the developer, I need to update things. But the graphic we get, so I'll maximize it a little bit. So I was looking at group on the x-axis, so we see that there's 2 levels for group. We already knew that from Easy Gray C. And there's 40 levels of ID, so there's 40 individuals in this. So clearly I collected this data in a not very temporally balanced manner, in that the first 20 people were all from one group, and the second 20 people were all from another group, assuming that data collection proceeded in order of the ID number. That may not be the case. But what's important from this is looking, everybody has the same amount of data. There's no differentiation in the color amongst these 2 groups. Maybe I want to look at the distribution of the sexes across the 2 groups. So I'm still going to leave, I'll do another call to easy design, still using A as the value being supplied to the data argument. I'll leave group as the value being supplied to the x argument. But now instead of ID on the y-axis, I'm going to put sex on the y-axis. So I can run that, and that generates a plot, which I'll maximize a bit to see it. So, as we expect, we get a 2 by 2 grid here, group on the x-axis, sex on the y-axis, and now we see a little bit of differentiation in color. Blue means more data, red means less data. Evidently, you can see this overall pattern whereby there's more females than males in my group. This is pretty typical of the types of populations that we get in our undergraduate subject pools. It kind of looks like that pattern is a little bit more extreme in the ADHD population than in the TD population, so there might be a little bit more of a gender difference in the amount of data that we have in the ADHD population. That can happen. Let's look at another way of, well, let's do another call to easy design, so another look at the data. We'll put now dot on the x-axis, arrow on the y-axis. So presumably dot and arrow are both manipulated variables that were manipulated within subjects. And we'll put group on the as a variable that splits the plot into different columns. So I'll select and I'll run, and that will generate something that I'll maximize. All right. So what I can see here is that, again, no differentiation in color. So both the groups got the same amount of trials, which we actually knew from the previous plots. But additionally, there's equal numbers of every possible combination of arrow validity and dot validity. So that's useful to know. For example, as somebody who generated this data, but also is familiar with the phenomena of spatial attention, I know that when there's equal numbers of valid and invalid spatial cues, that means that the spatial cue carries no spatial information. Participants would be just as good ignoring the spatial cue as they would pay attention to the spatial cue. So any effect of the spatial cue has to be an effect attributable to automatic processes that we typically call exogenous processes. But that's, this is just, again, a little toy data set, so you don't need to understand the theoretical framework behind it. So what I'd like to do next is go in this data frame. I've got, scroll back down. I know that there's a bunch of people in this data frame. Each person has an age, a sex, a group that they're assigned to. And while I'm later going to be interested in how their performance varies across the different levels of the manipulated variables dot and arrow, maybe I'm just interested in getting a picture of their overall performance by their mean RT and their mean error rate. So I'm going to expand my text file a little bit to have it all come up. So I'd like to generate some descriptives for each person. So what their age is, what their sex is, what group they're in, and what their mean RT and mean error rate is. So I'm going to use the ddply function. In the same way that the ldply function takes a list in, applies a function, and gives out a data frame, we are going to, with the ddply function, it's taking a data frame in, doing something to it, and providing a data frame out. The big difference between, other than taking in a data frame as the value of the first argument, .data, a big difference between ldply and ddply is that with ldply, you specify .data and .fun. With ddply, you specify .data, .fun, and then this other thing, .variables. .variables tells ddply how to split up the data frame to then run the function. So what we want to do is we want to, for each participant in this data frame, we want to summarize their data. So we want to iterate over participants in the data frame. So we give it a data frame, and we have to tell it we want to iterate over participants. So here's that dot period. I guess it's a function again. It's just a way of telling ddply that the ID column is inside of the A data frame. And what's going to happen for each, what's going to happen is that ddply will first take A and split it up into however many chunks there are that specify unique levels in this column here. So each chunk is going to be a different subject, a different ID. And then it's going to apply the function that we define here to each chunk, which should yield a data frame. All those data frames are going to be concatenated at the end and given to us as the result of calling this function, which we've then asked it to store in a new data frame called Descriptives. So what is the function that it's going to apply to each participant's chunk of data? Well, we're creating an object, a temporary object, because it's not in the global workspace. It's being defined inside a function. We've got an object called toReturn that's being defined. So the name's arbitrary, but it's being chosen to imply that this is the object that's going to be returned at the end of the function. And the object is a data frame. Well, ddply wants to have data frames at the end. So it makes sense that the toReturn object is going to use the data frame function to create a data frame out of whatever information has been passed into that function. So the function's first argument, or the function's only argument, is x. So what happens when the functions run the first time, the value inside of x gets set as the first piece of data that ddply has found by splitting the data specified here by the unique levels of the variables specified here. So the first time it runs through, x is going to be set to the first person's data. So it's a data frame. So x will be a data frame. It will have all the columns that the original data frame had, but it will only have those rows for the first participant. So we know that in this data frame, for a single person, their age just repeats across the column. If we scroll up to when we took the head of A, first person, age 19, first person, age 19, first person, age 19. So to get that person's age, all we have to do is say, I'm going to create a column in my new data frame with the name age and assign into that column whatever the result of the thing on the right is. The thing on the right will say, okay, look at x, look at the age column within x, that's what the $ means again, and just grab the first element that you see. So it's the first entry in the first row of the age column for that first participant. And that will grab that single value for age for that person. And we can do this because we know that age just is constant in the column for a given person. Same thing with sex. We're going to add another column to the data frame. So when you're using the data frame function, you're naming columns, putting information in them, and then when you want to add another column, you just put a comma in between. So sex is a new column. Its contents is the first element of the sex column of that participant's data. Group, ditto. It's just the first element of the group column, because we know group is constant across a person. Now what I want to do is actually compute the mean error rate for a person. I know that a given person's data is stored in X for the running of this ddply, and it's called a ddply. So what I can simply do is compute the mean of all the values in their column called ER. So I say, go in the data frame X, look for a column called ER, and take the mean of that column, and store that into a new column in the data frame that we're creating to return called mean ER. We can do the same thing for RT. One thing that, again, when you're doing the type of research that I do in particular, you're mostly interested in only a subset of the RTs, only those RTs that, only a subset of the trials, only those trials on which people made an accurate response. So it starts off looking similar to when we computed mean error rate. We say, okay, look in X, look in the reaction time RT column within X, but I'm actually going to only take a subset of the rows within that column. The subset of rows is specified by just a single selector, because we've already told it what column to look at. We don't need, before we had a data frame and we had a row selector and a column selector. Here we have just a straight up column, so we only have to specify the row selector. So for the row selector, we say look in the ER column in X and see if that value that's in that column is equal to 0. So those rows that are ER is equal to 0 will be selected. Those rows whose ER value is 1, which means that they made an error, will be omitted. So we're using that as a selector for the different rows of RT, and then once we've got all those accurate RTs, we compute the mean and store that in a column called mean RT within the data frame that we're creating. So this creates a data frame with 1, 2, 3, 4, 5 columns and 1 row. So not a very exciting data frame, but what's going to happen, we return that data frame, and that's going to be stored temporarily in memory. And then ddply will automatically repeat this process, but this time collect the data from the second participant, and then the third participant, fourth participant. So it will have a whole bunch of collected data frames with these columns and 1 row, and when they're all combined together, we get a single data frame with these columns, but multiple rows, each row containing the descriptive information for a person. So is there any questions on this use of ddply? Yeah. So the overall data frame, A, has a column called ER. That column just tags whether a response was accurate or not, or I guess whether they made an error or not on that trial. All the columns that exist in the overall data frame will still exist in the X data frame, because the X data frame is just a chunk of the overall data frame. We've taken out just those rows corresponding to whatever subject we're dealing with on a given iteration of the ddply loop. So, for example, that X will have a column called age, and we just need to know the first value for that because it's constant. Well, what it's going to do is it's creating a new data frame with 5 columns, summarizing the data from the, I guess, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 column larger data frame. So the larger data frame has an age column, a sex column, a group column. It also has a block, trial, validity, but we're not actually interested in those for the current time. We are interested in the ER column and the RT column, and what's happening, that ER column has as many observations as a given person has trials, and we just want to get the mean of those observations. So that will just give us a single number that we then associate with that person as their mean error rate. Ditto with mean RT, although it's a little bit nuanced here because we further select only those rows within that person's data that correspond to accurate observations. So we get a single value for that person's age, a single value for that person's sex, a single value for that person's group, a single value corresponding to their mean error rate, and a single value corresponding to their mean accurate RT. So it might be helpful to actually run it and then just show what the result is, and that it might be a little bit more intuitive. So I'll run this. I'm actually going to resize my window a little bit so that when I run the print, well, we actually don't have to run the print. You can run the print, but you can alternatively look at your workspace and click Descriptives, and now you'll get what the data frame that we just created. So here you can see there's the 5 columns that we intended to create: ID, age, sex, group, mean ER, and mean RT. And for each person, we have an entry and we have a row. So there's 40, should be 40 rows in this. You can see we've grabbed each person's age, each person's sex, each person's group, and then computed their mean RT and mean error rate. Gotcha. So if you look at A, well, I'll actually still in the data view. Yep, data viewer. If I look at A, ID1 has a row. For trial 1, block 1 trial run, it will have a RT and an error. ID1 also has another row for block 1 trial 2. So ID1 has actually a large number of observations. So that's how we're getting the yeah, so there are a good, let's see, 32 trials, I think times 10. So I think each person has 320 values in their error rate column and 320 values in their RT column. So we're computing a mean across those. Alrighty. So we've got this descriptives object now. We might want to just check out features of our data. So I've showed you easy précis, and I can, example 2, I'm going to add a little bit of code and just show you easy précis of descriptives. Type it correctly. Shows you ID is a factor, 1 through 40, age, 8 unique values, 18 to 25. So far, these ones are not any more informative than the ones we had than the input that we had, or sorry, output we had from the easy précis of the overall data frame A. But now we get some information here about the variability of the mean error rate and the variability of the mean RT. So the fastest person's mean RT was around 400 milliseconds. The slowest person's mean RT was around 600 milliseconds. Another way of getting a summary of all the different columns in a data set is using the built-in function called summary. So I can run summary, and it's going to have very different looking output. For each column, it's going to have some sort of way of summarizing it. For columns that are factors, you'll just see a list of the first 6 factor levels and how many rows that factor takes up in the data frame. ID, well, there's only going to be 1 row per level of IDs, so they each have 1 there. But it tells us, in addition to these 6 levels, there are 34 other levels of ID. For a total of 40 levels of ID. Age is a numeric variable, so it's actually going to give us that same minimum and maximum that we had up in EasyPrayC, but it gives us a little bit more information. So it gives us the first quartile, the median, the mean, and the third quartile. So you get a sense of the distribution a little bit more from that. Sex, again, a factor. It's going to list the number of rows associated with each level. So female, there are 25 females, and male, there are 15 males. With group, shows there's 20 group individual rows from the TD group and 20 rows from the ADHD group. And again, we've got a couple of numeric variables, mean ER and mean RT, and we'll get the some quantitative descriptors of those, the distribution of data in those columns. So the summary view can be useful as well. It sort of supplements the information that you get from using EasyPrayC. If you want to just look at a summary of data from, say I want to just look at the summary of the ADHD group. So I want to see about their age range and reaction time range and things like that. What you want to do is you want to run a summary of descriptives, but only a subset of the rows of descriptives. So I'll actually make this quite wide, because this is a quite wide command here. So we're using descriptives as a data frame. We're using square brackets to subset the data frame, and whenever we're subsetting a data frame, we need to have a row selector on the left-hand side of a comma, and if we want one, a column selector. Here we want to use all the columns, so we can omit the column selector. But the row selector, what we're going to do is we're going to say, look in the descriptives data frame, look in the group column within that data frame, and only grab those rows whose value in that group column is equal to ADHD. So we can run that, and I'll resize this again so that it actually prints nicely. This shows that, oh, well, our ADHD folks, they range from 18 to 25. Sex ranges 13 to 7. Sorry, ranges. There's 13 females and 7 males. Group, well, we know there should be 0 TD entries in this subset of the data, and 20 ADHD entries. And we can get an eyeball the error rate distribution and the reaction time distribution. The next row in the code here simply does the same thing, but selecting out only the TD, the folks in the TD group. So I'll select that and run. And we can see we've got just the TD people, no ADHD people. Their age range is the same, so maybe I did some matching or something. We've got 12 females and 8 males. And you can maybe eyeball the error rates and RT distributions. So I've showed you EasyPrayC, that gives you sort of an overall view of the type of variables, and in the data frame summary gives you a slightly more nuanced or slightly different view, slightly different information. You can use the Easy Design function to get a graphical view of the balance of data in your design. Something that I haven't told you about is the table function, although I vaguely recall using it yesterday. The table function is essentially the same thing as the Easy Design function. The Easy Design goes in and for a specified set of variables counts how many rows there are in the data set for each unique combination of those variables, and then visualizes that. Table will do the same. It will count the number of rows for each unique combination of variables you tell it, but it will just spit out the raw numbers as a table in the console. So if you don't want to take the time to have Easy Design generate a full graphic, if you want to actually see the numbers instead of the colors, what you can do is use the table command. So I'm going to actually add some hard returns in here. So I'm going to say, I'm just splitting the arguments that I'm passing the table across different lines so that it's easier to see. So what I'm doing, though, is I'm saying, so I'm going to call the table function. One argument that I'm passing is the column sex within the descriptives data frame. And I'm also giving it the column group within the descriptive data frame. So what this is going to do is it's going to count all the rows that are in the data set for each unique combination of sex and group. So how many females are there in the TD, how many males are in their TD, how many females are in the ADHD, how many males are there in the ADHD, and print a little table of that. So if I run that, we'll get a little table, and we can see there's 12 females in the TD, 8 males, 13 females in the ADHD, 7 females. So if you recall back to our plots, actually I think we can bring up our plots. Let's see. I'm going to click that plots thing and maximize it. And one thing I haven't showed you about this plots area is that you can go back. You can see previous plots that you've created. So I'm going to click back, and that brings us to that sex by group plot. So this is the exact same information that we have in the table we just created. The counts are, because we did this call to easy design on the raw data, it's counting all the rows, so the counts are a little less meaningful than counting just the people, which is what you'd be doing in the when you use the descriptives as the thing that you're looking at. But you can see that I said before, it looks like there's a little bit more extreme gender disparity in the ADHD group than in the TD group, and you can see from the table here that it's just that there's one more. There's in one group than the other. I should probably show you a little bit more of this plot area. Yep, plenty of time. So I just showed you that you can use the backwards and forwards to look at plots that you've already created and then created new plots. So you can cycle through the plots that you've created. You can, of course, zoom. I think this will create a new window. So you can resize to zoom, but you can also press this button and it will create a new window that has that in. And you can resize this window and it should dynamically resize that plot. So if you don't like having the plot stuck in a window here, you can, or stuck in this pane, you can put it in a new window. One downside of that is that when you go back to RStudio, it's now in the background. So I'm just going to close this plot window. You can also export directly from here. So you can save the plot as an image or save the plot as a PDF. Saving a plot as an image will save it in a manner that means that there's, it's encoding the information as pixels. So whatever size you have it in this image, it will, it may actually ask you, let's see, it will ask you what size it should be in width, how many pixels in width, and how many pixels in height. It will also ask you what general format you want. Oh. Okay. So you can save it. So if you save it as PNG, JPEG, TIFF, BMP, or BMP, all of those are bitmap files. So there's literally pixels that are on the screen. With pixels, pixels are a little bit more standard in the sense that you can just put it straight up on the web, and that would be viewable by anybody. But a problem with pixels for publication is that if you want high-quality printing, pixels, as you zoom in, they'll get bigger and bigger, and your images will start to look blocky and low resolution. So for publication purposes, I always save in what's called a vector graphic format. So SVG is a vector graphic format. So is PostScript. I rarely actually use either of those explicitly. What I do instead is I tend to use the export to PDF. PDF will automatically create a vector graphic format. that's infinitely zoomable. So the more you zoom on something, it's not going to look any more blocky. It's just going to be nice and crisp. So you can change the aspect ratio of the plot this way, and get a little preview of what the file is, and change the directory of where you're saving. Let's see, what's this? You can clear all the plots. That would just mean that you can't go back and forth. I don't see any reason to do that, really. Or remove the current plot from your list of things that you can go back and forth through. And I think this will refresh the current plot, so I think it will just replot it. I'm not sure why that's useful. So that was just a slight tangent to show you about this plots dialog here and how you can go back and forth, you can zoom, bring up a new window where you can export to files. Usually you want to export to a vector graphic file, which is, best one is PDF because it's pretty universal. So back to our code here, we were looking at different ways of, looking at data frames. We created this summary data frame descriptives that gives us some summary information about each person in the data set. And I showed you, in addition to the now familiar easy précis, we've got the summary function that gives us a slightly different view, different way of summarizing the information in that data frame. I showed you the table function, which is a way of getting a, I guess, text-based representation of the balance of data for a given specified set of variables in a data frame. Another thing I'd like to show you is your first graphic that you're kind of doing by hand. A lot of the graphics that I'm going to show you in the next session, they're going to be pretty automated. This section I want to do it by hand just to give you a little preview for what we'll be doing probably later this afternoon. So the graphic system that we'll be using is called ggplot. And it's a little quirky in the sense that to create a graphic, you first do a call to the ggplot command. And you don't give it any arguments. But you then add something to the result of what the ggplot command is going to produce. And what you add is whatever results from this call to the layer command. So the layer command is a way of, I'll explain this a little bit more, but what the layer command is doing is I'm telling it, I'm going to create a plot who has a geometric object that's going to be text. The data that layer is going to look at is going to be the descriptive statistics that we're interested in. So that descriptives data set. And I'm going to map some columns to aesthetic attributes in the plot. So I want to make a plot where on the x-axis I've got the error rate, the RT. On the y-axis I've got the error rate, and I want to have a plot of the individual participant labels. So and I want the labels to be colored according to the different groups that the participants are in. I'll tell you why I want to do all this after I run this, but as I said, it's pretty straightforward to see how I am achieving that mapping of aesthetic attributes to columns in the data. If I want to map the x-axis aesthetic attribute to mean RT, I just add it as x equals mean RT. Y equals mean ER means that I'm putting mean ER on the y-axis. I've asked it for a geometric object of text, so it's going to plot little text on the screen, and to say what the text should be, say what the text label should be, I tell it to map that to the ID column, and finally to say the color of the text should be mapped to what group each ID comes from. I say color equals group. One note here is that you don't put the period parenthesis around that. The reason is that, that's just something you have to remember. You can think of it as AES will automatically take care of that. You're specifying the mapping within something else that automatically takes care of the fact that you're referring to columns within the data frame that you provided as the value for the data argument to layer. So if I run that, it's going to create a plot, and maximize it so it plots a little more nicely. And what this is doing on the x-axis is mean RT, on the y-axis is mean error rate. The different groups are colored differently, so I can see that all the red dots are the typically developing participants, all the bluish dots are the ADHD participants. When you have the type of data that this project represents, where people are making decisions as quickly as they can, and they can be accurate or inaccurate, you tend to find that participants should have this general, I guess, you should have a general negative correlation across people with regards to how many errors they make and how fast they go. People who go really fast should make more errors. People who go really slow should make fewer errors. So what this value up here, it says 40 up here. This means that participant number 40 was really fast. They had a mean RT, sort of around 400, but they also had an error rate that was about, I don't know, looks like about to be 26, 20, or 27, 28%. And indeed, if we actually look at that Descriptives data frame and look down at participant 40, yeah, they had an RT around 400 and a error rate around 28%. So this gives you a sense to see. I usually look at a plot like this to see if there's any outliers. So for example, this 3 seems like it might be off this diagonal pretty substantially. This just happened, I happen to have an expectation with regards to the relationship between the mean RT and the mean ER variables. But the point here is that you can create a nice little plot to investigate the relationship between any variables visually. Let's see, this next section. Okay, the next section actually shows how to quantitatively evaluate that relationship that I generally described here. So if I want to just, ignoring group, look at the correlation between mean error rate and mean RT. The next section shows a use of core.test. So this is the first time we've actually encountered an actual analytic tool. So far we've just been doing data modification and summarizing, but here we've got an analytic tool. We're going to do a correlation test. And what I'm going to try to test is the correlation between the mean RT column in the Descriptives data frame with the mean error rate column in the Descriptives data frame. So I can run that, and I'll maximize my output console here. So we get, I'm going to expand this a bit. So we get some output here. Pearson's product moment correlations. So there's different types of correlation that you can do. Those are triggered by different arguments to core text, core.test. We didn't try to modify, we didn't supply any extra arguments to core.text, so it used the default, which is Pearson's product moment correlation. If you want to see what the alternative options are, we could go to help and core.test, enter, and we'll get a little help page. And we'll see core.test. It's got a bunch of different arguments. We've got one that talks about whether the alternative hypothesis is two-sided or a one-sided alternative. Whether the method is we can do a Pearson correlation, a Kendall correlation, or a Spearman correlation. Down here is the explanation of all these things. So that's why I know that method is the thing that specifies Pearson, Kendall, or Spearman. And, so yeah, let's go back to our output though. Yes. When something's specifically easy, it says easy at the front. Yeah, so core.test is built in. So I'm going to come back down to our result here. So it says Pearson product moment correlation, so it's just telling us what type of correlation it's computed. It tells us what data it was computing things on, so the mean RT column in the descriptive data frame, the mean ER column in the descriptive data frame. It gives us the t value, the degrees of freedom, and the p value associated with the correlation test. It tells us what the what the alternative hypothesis it was evaluating was. So the alternative hypothesis was true correlation is not equal to 0, which is a way of testing when you don't know whether the correlation is going to be positive or negative. It also gives you, in addition to the typical sort of null hypothesis testing values, so your p-value, it also gives you a confidence interval, 95% confidence interval, which could be used in a null hypothesis testing way or not. But you can, in the same way that this is saying the p-value is very low, it means that the data is very unlikely under the null hypothesis. It's similarly saying that the 95% confidence interval, 0 is not included in the 95% confidence interval. So both of those are the same, are different ways of saying the same thing. That is, the data is unlikely under the null. We probably want to reject the null as a account for this data. And it gives us, here it says sample estimates. That means what is the sample correlation. And so it gives us negative 0.43 as the sample correlation, which I said that I expected a negative correlation, and visually we definitely expect a negative correlation. And so what we are saying here is that the correlation is negative 0.43, which is, we'd say, is significantly different from 0, and we put our t-value, df, and p-value there. And that's how one would maybe go about reporting that. So, yes, there is. Do I have that in a later example? I do not have that in a later example, but we can do that right now. It's pretty easy to do. So I'm going to copy this core.test example. Make this bigger. So copy the core.test example and paste it right below it. So I want to rerun the correlation test within each of those two groups independently. So I can, I want to subset so I'm saying I want to grab the mean RT column in the descriptives data set, but only those rows that correspond with participants that were in the ADHD group. So I want to say descriptives group equals, and then capital ADHD, all in quotations. So once I have that, I can just copy it and paste it there. So you should have mean RT column within descriptives, subsetted by this thing here, which is saying look in the group column within descriptives and only select those rows whose value in the group column is equal to ADHD. Yeah? Yes. Yep. So let's find something up above where I put a comma. So up here, I wanted to do a summary of the whole descriptives data frame. And I had descriptives, and then immediately I had square brackets. So when you're trying to subset a whole data frame, you need to have square brackets, and then something to tell you about selecting columns, and then a comma, and then something to tell you about selecting, the thing on the left of the comma is what tells you about selecting rows, and the thing on the right of the comma is what tells you about selecting columns. Here, I didn't put anything to tell me about selecting columns, so the default behavior is that I'll select all columns. So that's for selecting a whole data frame, for subsetting a whole data frame. But down here, when I'm doing my selection, or my subsetting, I'm subsetting a column within a data frame. So I've already selected column. So it knows what column I want. So now all I have to do is tell it what rows that I want. So that's why I don't have to have a trailing comma at the end. Indeed, if I put a trailing comma at the end, it will give me an error saying that there's no columns within that column. So I'm going to select that, resize my window a bit, and run. So within the ADHD group, we've got, again, a pretty similar sized correlation that comes out with a p-value that's a little bit larger p-value, but that makes sense from the perspective that we have fewer people contributing, fewer data points contributing to the estimate. So we can go back to our code. So we've looked at whether that relationship holds within the ADHD group. Now let's see if it holds within a TD group. So I can copy this section here and paste it again below. And instead of ADHD, I'll just say TD. Yep. All right. Do you have, let's see. It's likely that you've left out one character somewhere. So likely, possibly, you've left out a quotation mark somewhere, or maybe you put, well, if you put a single. Okay, gotcha. All right. So we should be able to easily copy the earlier subsetted correlation test and paste it and then modify it to look at just the TD group. And if I resize and show, oops, I can run that. Exactly as you indicated, seeing by eye. Wow, that correlation seems pretty strong in the context of the ADHD group. In the context of the TD group, it seems not so strong. We've got a correlation of -0.1. So, and indeed our inferential null hypothesis testing stats seem to indicate that the data is pretty likely under the null. Pardon me? Yeah. And our confidence interval thoroughly includes 0. So if we actually pull up that graphic again, which is under plots, yeah, so the bluish, they tend to have this nice spread along the negative diagonal, but the red TD, they more form a nice circle. So that makes sense. Now, if we were to, let's see, I'm going to stop pretty soon, but I will say that what we just did would not necessarily be publishable as such. So what we've done is we did a test of a correlation in one group, and then a test of a correlation in the other group, and we found a pattern, a difference in the pattern of results. In one group, we found a pretty strong correlation. In the other group, we didn't find a pretty strong correlation. Lamentably, it is very common for folks to publish precisely that analysis. You say, I did a correlation in one group, came out, correlation in another group, didn't come out. It turns out that that's a fallacious way of doing statistics. There's a nice paper that came out recently where they actually tabulate the rate at which people do these across different journals and disciplines. But what you're trying to say, so we computed a correlation test because we weren't satisfied with just eyeballing the data. In the same way that we wanted a quantitative test of what our eyes were telling us, you still need a quantitative test of what logic is telling you. That is, what you've done is you've done 2 tests, had slightly different results from those 2 tests, and so you're applying logic to say, oh, there must be a difference here. But that's not a quantitative statement. What you need to do is explicitly test whether the correlation is stronger in one group than the other. Sorry? Well, you can do it that way, or you can explicitly evaluate. So the way to do it is, let's see. So what we're going to do is create a, instead of core.test, test, we're going to create a object we'll call my LM. So inside my LM, we're going to store the results of calling the LM function. The LM function is going to take a few arguments, so I'm going to spread it across a few lines. It wants a data argument, so I'm going to say the data is the descriptives. And it wants a formula argument. So the formula is going to be, let's see, let's do it as ER, and then the tilde character. You have to press Shift, and then there's a squiggly line right next to the 1 key. So ER is a function of, oh, actually, there's no column called ER in the descriptives data frame. It's called mean ER. So we want to look at mean ER as a function of mean RT. And the way to tell LM, the way to tell M that you want to look for an interaction is to do a multiplication when you're specifying a formula like this. So we want to say mean RT by group. So what this is doing, it's going to evaluate the degree to which mean RT predicts error rate, the degree to which it predicts error rate, but also the degree to which you need to add group as an interaction in that relationship. Linear model. So we're just like our correlation tests assume, we're assuming that mean RT and mean error rate, mean ER, have a linear relationship, which in this scenario is probably, well, the best we can do at this stage. So once we've called this myLM, what we can do is, let's see, I haven't used things this way in a while. I think this is what we want to do. So you call the ANIFA function on this new object that you've produced that contains the result of this call to LM. And that should print something out, so I'll resize things so I can see. Go back down to the bottom of my output and say go. Aha! So what's happened here? So this gives me an ANIFA output table. It tells me that, yes, there is an overall correlation between the mean ER and mean RT. If we take this F value, I think there's a way, if you take the square root of this F value, you get an error? Okay, so let's look at our call again. You said data equals descriptives, and then you have a new line with a comma. Forgot the comma? Oh, okay. All right. All right, so if I actually scroll up and look at the first correlation that we did, it has a t-value of negative 2 points. No, it's not going to be precisely squared, is it? Well, yeah, actually it is. Yeah. So it has a t-value of negative 2 point something. If I square that, well, I've only taken a portion of the full value, but it's pretty close to the value of the F value that's being printed here. Indeed, if I had the full hundreds of digits of decimals accuracy in square before I did the square root sign, these would be identical. So this just replicates our overall test of the correlation. We actually have a line here asking if group predicts ER. So that would just ask, is one group have a higher error rate than the other? It seems that that's not the case. Pretty low F value, pretty high P value. And additionally, there's no interaction. So even though the separate tests tells us that, hey, that there's a relationship in one but not in the other, we can't say that the groups differ in the degree to which there's this correlation. So I didn't intend that to be a lesson of this section, but since we started investigating this correlation in the different groups, I couldn't resist demonstrating that. It's a common fallacy for statistics for people to only report the test of the separate groups and not back up their conclusion from logic with quantitative stats. We could look at the confidence intervals from the two individual tests. The confidence intervals for the, I guess this was the typically developing group, was -5.2 to 3.4, and the confidence interval for the ADHD group was -7.7 to 0.2. So if one were to just imagine 5.2 is pretty close to 7.7. So there's quite a bit of overlap between the confidence intervals of those two groups. That would give us suggestion that our logical conclusion that there's a difference between those two groups is of the other. Yeah. Yeah, exactly. Yeah. And yeah. Well, yeah, we can talk about the philosophy of that later. The word proved in and of itself is troublesome. So is there anything left here that I want to look at? Oh, yeah, to finish off, you may not use it that frequently. So we had one way of showing the correlation with the plots. There's actually a slightly easier way to plot that. It won't show, if we just want to show the overall plot of the relationship between RT and error rate, which we've established does have support in the data. We're not going to have individual points as labeled according to individual participants, and we're not going to have the color differentiating the different groups, but the EasyCore function will allow us to visualize that same correlation, but with some extra data in there. So what I'm going to do is I'm going to expand this so that you can see this call to EasyCore because it's very long. The reason why it's long is because I'm taking the descriptives. EasyCore wants at least one argument. So we want the data argument to have as its value a data frame. So we're using the descriptives data frame, but we want to just give it only those, the whole data frame, so all the columns, sorry, all the rows. So we've omitted the, we're subsetting the data frame, we've omitted the row selector, meaning that we're going to grab all the rows, but we only want the subset of the columns. And those columns, if you remember from yesterday, one way to select columns using the selector method is to create a list of the columns that you want. So I want the mean RT column and the mean ER column. So it creates a vector of the columns that I want by using the C function. And then use the in comparator to say, for each column for each name of each column, is that column in this list that we just created. So this selector will make it so that we're subsetting and grabbing only the columns mean RT and mean ER. So if I select that, then I'm going to resize my windows because I want to have a plot in a second. And I'll run it. I'll have a plot. It's going to look kind of funny. So this is a correlation matrix. It's a graphical correlation matrix that gives you more information than the typical correlation matrix. So the diagonal just puts labels for the different variables that you're interested in. So here we only have two variables in our correlation matrix. So those two variables, their correlation is expressed in the cell that they are both connected to. So if you go up and go sideways, they're both connected to this cell. So the correlation is -0.43. The fact that it's colored red indicates that a test against 0 is would reject 0 as a null hypothesis using null hypothesis testing in an alpha of 0.05. This plot down here plots the bivariate distribution of those two variables. So error rate would be here in this scenario. Since error rate's in this, it would be on the x-axis. And RT, since it's connected to this plot's to its side, it would be on the y-axis. And the white thing here describes the univariate distribution. I'm about to show that. Okay, so the white here describes the univariate distribution. So what is the distribution of error rate? And this is what it would look like generally. And you can eyeball that for non-normality or outliers, and eyeball the mean RT distribution for non-normality or outliers. And you can also eyeball the bivariate distribution here for outliers that might be particularly influential. It's pretty boring when you only have two variables. When you have many variables, it becomes incredibly informative. So I will show you the next command, which is another call to EasyCore. But this time, I'm still using descriptives, I'm still using all the rows, but I'm going to get just a subset of the columns. Same as above, mean RT, mean ER, but now I'm adding age in there as another descriptor, or sorry, another column that I want to select. So I will select that little bit, I'll resize, and I'll run, and resize this again. So if you just looked at these bottom right 4 areas, that would be the exact plot that we just showed, but now we have many more cells in our thing. So again, the diagonal labels the variables we have. The white underneath of it shows the univariate density of the data for that variable. If you look in the upper right corners, upper right half of the matrix, it tells you the correlation between any combination. So age versus ER, that's its correlation there. Age versus mean RT, that's its correlation there. And of course, we're familiar with the age versus, ER versus RT right there. You can see that these two aren't red. So if one did a null hypothesis test with alpha of 0.05, that would not come out as a significant correlation. And we can indeed see if we want to look at the age by error rates bivariate density, we can look at it down there. That's the bivariate density. Here's the age by RT bivariate density. And they don't look like there's much of a relationship. So this gets really useful when you have really large sets of descriptive statistics, and you can see just patterns of correlations across things. You can eyeball for outliers and eyeball for non-normality of things. Alrighty, I think I'm going to stop for lunch there. See you guys all in an hour.